Hello and welcome to my talk, How to Bring Your Programming Language to WebAssembly. But first, a little bit about who I am. I am Wouter van Oortmersen, originally from the Netherlands, though now living in San Francisco. I work on WASM tools for the Google V8 team. That means I work on WebAssembly features in LLVM, but also Wabbit, Binarian, and others. I also created the WASM decompile tool, and I'm the champion and, of course, tools implementer of the Memory64 proposal. Generally, I'm a huge programming language enthusiast. I've designed and implemented more languages than I can count, and I'm excited to see as many languages as possible come to WASM, which is the motivation for this talk. But first, what is so special about WebAssembly for programming languages? WebAssembly promises to democratize programming languages. With an easy-to-target executable format, once a platform supports WASM, it can run each language equally. This means programmers are no longer tied to the language that the platform prefers, and new languages can compete on equal footing with established ones. Hooray! But is it really that simple? There are a number of options to consider in how a language can target WebAssembly. This talk attempts to give an overview of some of them. So WASM isn't a very standard virtual machine. WASM is beautifully simple: a linear chunk of memory, an implicit stack, some instructions that operate on it, and that's largely it. Like a slightly more elegant, safer CPU, it comes with no runtime, no operating system access, no built-in functions. It doesn't even know how to print anything. That simplicity is thus also its downside. We'll need to figure out how to implement your language's runtime, and as it turns out, that is not trivial. Being a safe CPU also means it's incredibly low level. It only knows memory locations and doesn't even know what a struct is or how to allocate one. But with that comes a lot of freedom, in that it is less restricted in what languages can run well on it than past VMs. First, let me give you an overview of the main tools I'll be referring to. Wabbit is a very comprehensive suite of tools that can be used to disassemble, decompile, verify, assemble, and even interpret WASM code, and should be the first thing in your tool belt you reach for. Binarian is another tool set that is usually used as part of Inscription, but can also be used standalone. One of the most valuable parts for a language developer is that it contains a standalone WASM optimizer, WASM opt, which means less work for you to make things run fast. You will likely want to run this on your output no matter how good you think your compiler is. Then, of course, we have LLVM with Clang and LLD, the tools that turn a range of popular languages into optimized WASM. But likely you won't use these directly. Instead, you may use Emscripten, a full C++ toolchain that builds upon Clang, LLVM, LLD, Binarian, and provides browser API compatibility layers. There's quite a few reasons why you might want to depend on Emscripten to generate your WASM, as we'll see below. So what options do you have for targeting WASM? This is assuming you're writing a compiler where you want to generate WASM instructions for your language constructs. You could target the .wasm format directly. It is a binary format, and though writing it out yourself may be non-trivial, it is also the path that allows your compiler to function without relying on an external toolchain. You could try to avoid dealing with binary files by writing the WASM text format .wat, and then have the wat to WASM tool, which is part of Wabbit, do the heavy lifting for you. But that is currently restrictive, as it doesn't allow you to create a module that is linkable against other object files. Nope, if you want to do it right, you need to generate a binary file. We'll talk more in a bit about how to do this yourself. Of course, LLVM is an existing compiler that so far has had the most amount of work put into its WASM backend. Targeting LLVM IR, which you can do in text or via API calls, is not actually simpler than generating WASM, but it does save you having to generate the binary format, and you get LLVM's full suite of optimizations to run on your code. These optimizations likely go beyond what even the standalone Binarian tool can do, so this path is recommended if you want to squeeze the absolute last bit of speed out of your language. You'll need the LLC tool from the LLVM project that goes from the .ll text format to a linkable wasm.o file, or directly talk to the LLVM-C API. You'll also need the WASM-LD linker, the variant of LLD that understands WASM natively. Does LLVM-IR sound too low level for you? Of course, you can also generate WASM with the popular technique of just outputting C or C++ and letting Clang deal with the details. This gets you pretty much the same pipeline as described above for LLVM-IR with less effort. The downside? You'll need an even larger tool chain that includes Clang, which is much bigger and slower beast than LLC, and access to C++ includes and libraries. Also, you now need to be much more careful that C++'s pitfalls like undefined behavior and platform differences don't accidentally end up as features of your language too. If you go down this path, you can work directly with Clang and WASM-LD to generate WASM modules, but you might also consider relying on Emscripten instead, which is the batteries included version of this path. If your language is an interpreter instead, this is of course a lot simpler, and you likely just need to look into how to build your interpreter with Emscripten, assuming it's written in C or C++. However, since WASM is all about efficiency, I'd recommend looking into ways you could turn your language into a compiler instead. You might ask yourself, if there are any other simpler languages you can target? While there are other languages targeting WASM, they can't really compare yet in efficiency and maturity with the LLVM-based solutions I'll be talking about here. So let's talk about how to link with runtime code. Because chances are, if you have an existing compiler for your language, generated code for the program being compiled is not the only thing going into the final executable. You'll probably have a body of runtime code, memory managers, built-in functions, operating system bindings, support code for the data types your language supports, etc. Likely this code is in C or C++. How do we get this code into your final WASM module? You could go all in on the web way of doing things and rewrite all your runtime code into JavaScript. Now your WASM module just needs to generate imports to the right JS functions and you're done. Sounds good? No? Well, you might be tempted to want to output the runtime code right along with the code you're generating. But that means rewriting the runtime code in WASM itself, or in LLVM-IR. But writing WASM by hand will get a bit tedious for large amounts of code. Maybe we'd prefer to just compile the C or C++ runtime code as is. But this means that we need to link C or C++ code with your generated code, which means your generated code needs to play nice with the conventions of C++ linking and what WASM-LD expects. Those conventions are documented in the tool conventions repo, and they significantly complicate the generation of the .wasm format. With requirements for relocation, since we don't know where in the module our code will end up, and symbol tables, because we'll need to refer to our runtime code somehow. Besides LLVM, there aren't a lot of code bases currently that you could just reuse to do this for you. But fear not, if you still want to output your own WASM without leaning on C or LLVM-IR, I have gone through that exercise for you. Here's a fully self-contained C++ header-only library that's about as small as it gets for being able to generate WASM modules. Not only does it take care of all the gory details of the binary format, it is specifically written to generate all the linking information for you as well. And even if you're not using C++, it would likely be a good example to work from or translate one-to-one into another language. There's also a document that describes what this header does further with a simple example of its usage. Now, I'm about to show you how to use this header to generate a linkable WASM Hello World module start to finish. There's no need to understand the full details of what's going on here. The purpose of me showing you this is for you to get a feel of what is involved in writing your own binary, and hopefully agree that it can be pretty simple. So since this makes use of an API, this skips all the details of the binary format. But explaining that would be beyond the scope of this talk anyway. We start with a vector of bytes that will hold the resulting module when finished, and instantiate a WASM binary writer with it. A WASM module is divided into sections that must appear in a particular order and will be using the API to do so. The first section is the type section, or more precisely the type signature section, where we must specify every possible type signature we later want to refer to for importing or defining functions. Here we have just two, so it's pretty simple. We hold their indices in variables to make referring to them more readable. Then we specify our function imports. Remember, this being a hello world example, the print function will come from the runtime and is thus imported. And the calling code will be defined in this module. Note that the API call to specify it mentions the word link specifically. That is to indicate that this function does additional work to ensure that extra linking information is emitted later on. Next, we specify the functions we intend to define in this module. In our case, that's just main. Furthermore, we specify a linear memory we'd like to use. In this case, just one minimum page, which is 64K, with no maximum. And now finally, we get to the exciting part, the code section. We declare the function main with no locals in this case. Then we use these emit function calls over here to generate the actual instructions. The first instruction is i32.const, which would normally take a simple integer immediate argument. But here we have a special version of that instruction that will take care of tracking relocation information to be able to refer to the data section, where we will place the actual string to be printed. In this case, we refer to data segment 0 at offset 0. Then we perform the actual call to our print function. And since main is supposed to have a return value, we have another i32.const instruction, this time with a simple 0 value. Then we end the function. We could emit more functions here if we wanted to, but for now this will do. Finally, we have our data section. Here we add a hello world string as the one and only data segment. At the end, we call finish, which does the heavy lifting of emitting the linking custom section with relocations and symbols for anything used in the previous sections. Then the bytes contained in the initial vector can be written to disk as is, and we're done. So linking your runtime with this generated code should now be simple. Assuming we wrote the module to disk, now in the build file that builds your runtime code, you should have a command line, an EMCC or Clang invocation that is doing the linking. It should suffice to add our generated file to that command line. EMCC will take care of invoking WASM-LD for you, which will then link all the .o files into a single .wasm. WASM-opt will then optimize the result, and Emscripten will run further tools to generate JS bindings and such. This should all just work though. If it doesn't, you'll likely get linker errors at first. If you're developing a compiler, you may not want to rely on running the whole of Emscripten just to see if you're emitting the right thing. So here are some tools to check your work earlier and easier. First thing you should always run, and in fact should probably be a script to auto-run after your compiler, is WASM validate. We are terribly fortunate that WASM is very precisely specified and that all implementations that read WASM perform thorough validation. So you should lean heavily on this when writing a compiler. Passing validation means that most of the work in generating correct binaries is done. This is very much unlike generating, say, x86 or ARM code, where bugs in your code generation can be very hard to find. When things go wrong, you may want to dump the contents of your module to see what's inside. For compiler developers, I'd recommend starting with WASM objdump, simply because it gives the most low-level information with byte offsets for most things, which means it will be easiest to correlate with whatever is going on in your compiler or debugger. If your modules are working and you want to get a friendlier overview of what is inside, you could use WASM to WAT, which outputs the official WASM text format. Still, if your compiler generates a lot of code, the WASM to WAT output can get very verbose, redundant, and hard to follow. For the purpose of reading larger amounts of code, I'd recommend the WASM decompile tool that I wrote, which attempts to turn WASM back into something that looks a little bit more like C, Java, JS, and trends. It has a simpler, familiar expressions and tries to be clever about analyzing your memory excesses to turn them back into structs and such. There's a post on the V8 blog that explains it in more detail. As I mentioned, the binarian optimizer is likely going to run on your code, and you should make use of that fact by simplifying how you generate code. You can rely on calling small functions in your runtime that will still get inlined. You don't have to worry about allocating locals optimally, and slightly sloppy instruction sequences that compute something suboptimally will all be cleaned up for you. This is, of course, not magic. If you represent data in your language inefficiently or use a lot of dynamic allocation, no optimizer will clean that up for you. But wait a minute. We said earlier that WASM was hard because it doesn't have any built-in functionality. But now I'm linking in C runtime files that implement my print function and I can do whatever it wants. How does that work? So behind the scenes, Emscripten pulls in a version of libc, which in turn has its own syscall layer that calls into JS to implement things like I/O and even a full OpenGL functionality if you need it. This is of course very convenient, but it does result in a lot of magic and a lot of glue code. If you want to be more in control of things and maybe design your own way to communicate with JS functionality, you can certainly do so and use Clang and WASM-LD directly. There are already some great articles out there on how to do this, like this one by our own Surma, so I'm not going to go further into that. We've been talking mostly about C and C++ ecosystems so far, but of course Rust is another great language to work with in WASM and has the WASM BindGen tool to help you create bindings with JS. Now, for the final part of this talk, since we're all talking about bringing languages to WASM, I'd like to talk about language features, and in particular, how they map to WASM and its future features. First, let's talk about the elephant in the room, garbage collection. The various paths we have talked about so far all assume the use of linear memory, which work great for languages with manual, reference counting, or ownership-based memory management schemes. But what about garbage collection? You could, of course, try to port any existing garbage collector your language may have to WASM along with the rest of the runtime. But there's a few issues you may run into. For one, the actual WASM stack containing the WASM locals is not programmatically accessible to the program itself, so you can't use it to scan routes. The typical way you'd work around this is by using a shadow stack, a secondary stack that contains all possible routes in linear memory, which is pushed and popped along with the main stack. Such a stack is already in use in C++, for example, for any values on the stack whose address is taken. It works, but of course is less efficient than a native stack. Second, there is no robust way to track the lifetimes of JS values you may be referring to or from linear memory, especially once you account for cycles. So this will likely require some manual management. Alternatively, you can rely on upcoming WASM features. There is the reference type proposal, which provides special engine-managed types for referring to JS and other external values. The proposal for it has been fully accepted, and there is support for it in most tools and engines. Of course, Referring to values is only part of the picture. Beyond this, there is the GC proposal. This gives you full functionality for allocating engine-managed structs and arrays outside of linear memory, and thus should fully solve any cycle problems with the host and even with other WASM modules. It is testable today with current tools and in V8, but the spec is not finalized and things may still change. If your language is all about GC though, and this sounds good, I'd recommend getting involved. Next, interface types, which in my opinion is one of the most exciting features for new programming language enthusiasts in the WASM ecosystem. It is a way for a WASM engine to automatically generate translation bindings for data types at module boundaries. This essentially means that it allows programming languages that don't even know each other to work together, and for programmers to have the flexibility to compose their programs out of modules from any languages. As an added bonus, if languages happen to agree on representation, there's only little overhead, at most a copy. This is a key part of the puzzle for the democratization of programming languages I mentioned earlier. Sadly, while the proposal is being worked on, we're not very far with implementation work yet. Now, if you're porting over an existing compiler and you're relatively new to WASM, we should really talk about this four-letter word, goto. WASM is peculiar because it only allows structured control flow. Branches may go out to the start or the end of nested blocks, but may not jump into them. Many compilers use something like SSA, static single assignment form, as an internal format, or are used to target LVMIR, x86, or ARM, and thus rely on arbitrary branches in their final output. How do you get around this? Well, here are your options. So if you're going through LLVM, then this will be taken care of you automatically by rewriting these gotos into more elaborate constructs. However, this may still result in suboptimal code that you don't have control over. If your language doesn't have a very advanced backend, you could of course try to go straight away from your own structured representation, an AST, to WASM. Another option is linking to Binarian, which has an implementation of the relooper algorithm. So you can emit code in a way that Binarian will solve this problem for you, much like LLVM can. You could, of course, implement your own relooper algorithm. There's a paper that details the algorithm. Or you could help push forward funklets or multi-loop proposals in the committee that would reintroduce something goto-like into WASM. There are a lot of other future WASM features that should interest a language implementer, and I'll mention the main ones here briefly. The threads proposal mostly adds a lot of atomic operations for use on linear memory, upon which more high-level synchronization constructs can be built. It is widely supported and should be ready for use. It still does not provide any thread creation primitives. You're relying on JS workers in the background. Exception handling has been implemented for a while, but it has undergone changes in its spec up until recently. Emscripten can emulate exceptions using JS, but they're very slow. So if your language relies on them heavily, you really want the native support. SIMD is very mature at this point. It is, of course, mostly an optimization feature, so it should generally be possible for your language to either emit SIMD or scalar code for your language features. Multi-value is very interesting for languages that naturally allow for multiple values to be returned, or languages that want to be able to return multi-field structs or tuples efficiently. Tail calls are particularly a compiler-friendly feature, allowing you to emit continuation or trampoline-style code efficiently. The Memory64 proposal that I champion is quite far along in tool support in LLVM, but not fully supported yet by Emscripten, though will be the case hopefully very soon. It is particularly interesting to languages which are already 64-bit on other platforms. It even comes with an emulation mode in Binarian, allowing you to run a binary generated with the WASM64 architecture in LLVM on a WASM32 engine by still using 64-bit pointers internally. Finally, stack switching is an up-and-coming proposal that should be particularly interesting to languages that have coroutines, async await, or similar features. And that's it. Thank you for listening. If you have questions, I will be around right now to answer your questions on Discord, or tag me at any future time on Discord or on GitHub repos of the tools discussed. And of course, you can also find me elsewhere on the web. Thank you.